All right, and let's hope that today's taping goes more smoothly. Well, I'm not charging my phone also, so I have nothing to hit the stop button. So we'll see how that works. Okay. So one comment I want to make on the homework I just gave back, homework 3, a very common mistake was, so you have alright, so start with x equals b, but then you have LU decomposition with pivoting to PA equals LU. So to take advantage of it, you can multiply both sides by p. So PAX equals PB. So PA becomes LU. And if we say call UX equal to Y, that means the systems that you solve are LY equals PB, and then UX is equal to Y. So yeah, some people solve LY equals B. So whatever you do to the left side, you got to do to the right. And solving with L implicitly applies the row operations, like the adding one multiple row to another, to B, or to your right-hand side, but you also apply the row interchanges to both sides. So, okay. Yeah, because this is one of those problems where you know it's right if it worked out nicely, because the exact solution to the system is 1, 1, 1, 1. But some people did not get that. So. Yeah. Okay. Now, okay. All right, so continue with nonlinear systems. Today we're going to look at Newton's method. For systems of nonlinear equations. Okay. Now, so first a little mop-up from fixed point, which will help us transition into Newton's. A fixed point iteration on a system x is equal to g of x. Okay. Converges if you have this criterion satisfied, a Jacobian matrix of your function g. The norm of it is less than or equal to some constant row that is less than 1. So if you can show that this is satisfied on some domain D, and your initial guess is chosen from D. So under most circumstances, fixed point iteration is guaranteed to converge. Okay. Now, so the consequence of this is that and you can actually show this using basically a Taylor series expansion. That the error after k plus 1 iterations, the norm is bounded by rho times the error after k iterations. Okay. Now, actually, let's see. I'm going to fill in a couple steps here, because what is xk plus 1? That is g of xk. Because that's how the fixed point iteration proceeds. You plug in xk into g and you get xk plus 1. X star is equal to g of x star. Because x star is the exact solution. It's a fixed point. So it satisfies this equation. And when we covered fixed point iteration last semester for a single equation, we used the mean value theorem. But what you can do is, you can write this as a multivariable Taylor expansion. So this is equal to the Jacobian of G evaluated at x star times xk minus x star plus lower order terms. And what we have here, this is matrix vector multiplication. And then we have additional vector value terms here. So what you can show is, I won't get into details here, but this is, this Jacobian matrix is bounded and normed by rho on this entire domain D. That you get not bounded by that, bounded by rho times the error after k iterations. Okay. So what's happening is, from one iteration to the next, the error is decreasing by a factor of rho. And since rho is less than 1, the error is going to keep going to 0. So this is just a natural analog of what we saw last semester for a single variable case, where instead of having vector norms, we had, or matrix norms, we just had absolute values. Okay. Now, okay. And we can take rho equal to the maximum over all x in our domain of the spectral radius of our Jacobian matrix. So this would be a suitable value for rho, because the spectral radius gives a necessary sufficient condition for convergence. And we could also say that as x starts converging to x star, rho converges to, as our suitable value for rho would be the norm of the, sorry, not the norm, spectral radius of a Jacobian matrix at x star. So the smaller that spectral radius is, the faster convergence will be. So we need it to be less than 1, but smaller is better. Like, what if it's equal to 0.01, for instance? And the error is decreasing by a factor of 100 from one iteration to the next, and your iteration will be over very quickly. But what if we can get this multiplier to go to 0? That would be the ideal situation. So what if spectral radius would be, because you can choose G in many ways. If you have an equation, original equation you're solving, f of x equals 0, and we can transform in many ways into x equals g of x. If there's a way we can transform it in such a way that the spectral radius of the Jacobian would be 0, so you wouldn't even have a Jacobian at all at a fixed point, then what would happen to convergence in that case?
Instant convergence?
Not instant,
I mean,
because we covered certain kinds of convergence last semester: linear, superlinear, quadratic, etc. What kind of convergence is this? That's okay. We don't expect you to remember, Sarah, but yeah. Anyone who took the class last semester should know what kind of convergence is this of those different kinds.
this is linear.
It's linear convergence because the error from a previous iteration is raised to the norm is raised to the first power. If it's raised to a higher power, you have more rapid convergence. Okay. So what we'd like to do is see if we can choose G in such a way that we have a
Fixed point iteration has linear convergence. And
Generally,
No,
yes.
Generally, and Unix method used to have, Unix method had quadratic.
Quadratic, yes. So so if we choose G right, maybe we can drive this all the way to 0 and get quadratic conversions. Okay. So I'll refresh your memory, because apparently it's necessary, on what quadratic convergence means. Okay. So xk converges to x quadratically if the limits as k goes to infinity of the norm of xk minus x star, or sorry, xk plus 1 minus x star over norm of xk minus x star squared. Actually, I think the limit I used, the notation I used was c. So there's some constant c that this ratio of new error over previous error squared converges to a constant. So what that happens is that basically the number of correct decimal places essentially doubles from one iteration to the next. So in a typical floating point system, 4 or 5 iterations is going to be all you need in most cases. Okay. Now, in the n equals 1 case, which we covered last semester, you can solve a single equation f of x is 0 by converting it to a fixed point iteration, x equals g of x, where g of x is defined to be x minus f of x over f prime of x. And this is Newton's method. What? Okay.
Little g of x.
Yeah, so it plays a role of big G of x. So what I'm describing over there is solving a system of n equations and n unknowns, but I'm specializing and going back temporarily to the one-dimensional case.
Okay. So that is it is big G, but it's little g.
Yeah, it's little g for one dimension. So yeah. So
Big G's is back.
so bigger system, uppercase letter.
Yeah.
Yeah. Okay. Yeah, I guess I like to use capital letters for vector fields.
Okay.
Yeah. Okay. All right. So let's take a look at this. So convergence of fixed points in a one-dimensional case is usually linear. And what happens is the limit as k goes to infinity of the same ratio, but now I'm just going to use absolute values because we're back in a one-dimensional case. So for linear convergence, it's just xk minus x star down below to the first power. And the asymptotic error constant, and that's what the c is, turned out to be g prime of x star. So now that's, I say, usually linear. But now let's look at this g prime of x. So g of x is equal to x minus f of x over f prime of x. And let's look at g prime. So g prime of x, we'll just differentiate this. So we're going to get 1. And then we have to use a quotient rule on this. Fun. So we have f prime squared minus f f double prime over f prime squared. And you can simplify this quite a bit because this gives us a 1, which cancels with a 1 here. So once you simplify it, what you actually get is just f prime, or double prime, over f prime squared. So that's g prime in that case. So what is g prime of x star? If x star is the root. Because x star solves this equation, and it solves this one. So what is g prime of x star?
But f of x equals 0, so
Yes.
that has to equal 0.
Yeah, it's going to be 0. Yeah, just because of this makes everything go away. So, so we get quadratic convergence. Okay. For Newton's method, now that is the one-dimensional case. Okay. So now what we like to do is generalize Newton's method. So this is how on Monday we generalize fixed-point iteration from one dimension, one equation, to n equations. Now we want to generalize Newton's method in the same way. So if I write them both side by side, you'll see that the generalization is quite natural. Okay. So, in n equals 1 case, our fixed point function is, as I wrote down earlier, x minus f of x over f prime of x. Now, for a general case, solving n equations and n unknowns, I'll define our fixed point function g is x. Now, in one dimension, we just have a derivative, f prime of x. But here we have a matrix that's a derivative, our Jacobian matrix. We can't divide by a matrix. What do you do instead? What do you do with the inverse?
Multiply.
You multiply by the inverse. So, because now f of x, that is a vector quantity. So you have x minus the Jacobian matrix of g, evaluated at x, inverse times the vector f of x. So this is our new fixed point function. Okay. What?
Multiply by the inverse.
Yes.
I thought you were multiplying the matrix by its inverse, and I was like, how is that going to work?
Well, that'll give you identity. But
Yeah, that's what I was like, well,
Okay.
yeah.
No. Okay.
That makes sense, okay.
Oh, sorry. Not the Jacobian of g. Jacobian of f. Okay. That's what I want. Yeah, because it's f prime that's generalized to higher dimensions. Okay. All right. So now let's see what happens. So in one dimension, it wasn't hard to show that g prime at the root x star was equal to 0. Let's see what happens with Jacobian of g. Now, what I need to do is, okay, this is going to be a bit of a pain, but I have it worked out here. So, okay. All right. Keep in mind g of x has component functions, which I'll describe as g1 of x, g2 of x, down to gn of x. And f has big F has component functions F1, F2 up to Fn, all defined in the same way. Now, the Jacobian of F, that is a matrix that has as elements partial derivative of F1 with respect to x1, partial of F1 with respect to x2, and so forth, all the way down to xn. That's the first row. And then partial of F1, F2 with respect to x1, partial of F2 with respect to x2, down to partial of F2 with respect to xn. I need a bigger matrix. It's like Jaws, need a bigger boat. So finally, last row, dfn dx1, dfn dx2, dfn dxn. Okay, so that's our nasty Jacobian matrix. But in our formula, we actually have the inverse. So for shorthand, I'm going to say the Jacobian matrix inverse ij entry. I'm just going to refer to it as bi of x, bij of x. So we have these unknown functions bij. We know they're the inverse of Jacobian of f. So that there's no convenient formula for expressing them, because that would be really nasty, except in a 2x2 case. So we're just not going to bother. And it's okay, we don't actually need to. So with all this lovely notation, we're actually going to go to the trouble of computing the Jacobian of g and see what happens at the root. Okay. So the Jacobian of g of x. So first we have the Jacobian matrix of just x by itself. Well, the derivative of x is 1 in one dimension. So the derivative of vector x, the Jacobian matrix of that, it's just going to be identity. Okay. And then, actually, I've just written down the notes element by element, but I want to try to avoid that for as long as I can because it's ugly. Now, here we have a matrix that's a function of x times a vector that's a function of x. And we got to take the Jacobian matrix of all of that. So, good luck. And the way you would handle that is basically by using a product rule. So in other words, we have to respect the order of multiplication. It's this times this. So what's going to happen is, actually I may have to do this element by element, but we'll see. So in our product rule, we're going to, in our first term, we're going to leave this alone, the Jacobian inverse, and we're going to differentiate f, but that means taking a Jacobian matrix of f. So we get Jacobian of f inverse times the derivative of f. What is that? That's the Jacobian of f. So what happens? They become identity, which cancels with the other identity. Okay. So that's nice. But we have to finish off our product rule. Okay. And as far as what I have written out in the notes, and the result is definitely going to be a matrix. Yeah, and the things I have is written out element by element in the notes, but I want to see. What?
I thought like second derivative.
Well, you're not taking the second derivative because that's the inverse.
Yeah, so that's one thing. Now the thing is, yeah, because they are inverse of a matrix of first partial derivatives. Okay.
But the entries are bij's, so.
Yeah. Yeah, and actually what I'm trying to see is what's the easy way to express what I have here on an element by element level. Okay, because we're taking the derivative with respect to each variable. Okay, so the IK entry is itself a sum. Okay, so I'm going to write it in the simplest format I can, which is still not very simple. But I'm going to indicate what matrix this is by entry. So we're going to I'm going to show you the IK entry of this matrix and try to express it as simply as possible. So it's actually going to be a sum over J of derivative with respect to x k, because keep in mind, whatever variable we're differentiating with respect to indicates the column. Like first column is with respect to x1, second column with respect to x2, and so on down to the last column with respect to xn. So this is going in the kth column of this matrix. We're differentiating with respect to xk. And what are we differentiating? Bij. Now, and this is being multiplied by fj. And all of this is evaluated at x, whatever x we have. And this makes, okay, so really what's happening, this is, okay. This is an element of, so we're taking the ith row of the inverse Jacobian, and then we're taking the matrix vector product with f, but then we're differentiating all of these with respect to xk. So, in fact, I can describe on a column by column basis what this matrix looks like. So this is, so the first column will be derivative of Jacobian of f inverse with respect to xk times f. Because, so in other words, if you take all the entries of this inverse matrix and differentiate them with respect to xk, then you're multiplying that whole matrix times f. That's your first column, or k equals 1 in this case. Second column is derivative of the same inverse with respect to x2 times f. And so on, all the way down to the last column, derivative of Jacobian inverse with respect to xn times f. So that's what this matrix looks like. And it makes sense when you think in terms of what the product rule is doing. In a product rule, first term, we differentiated that, but not this. And that's how we got this term right here that canceled with the other identity. The other term, we do differentiate this and not this. And what you get is quite a monstrosity. But fortunately, for our purposes, it's going to be a lot easier to work with than you think. Because now, what we really care about is what is a Jacobian at the root. Well, these terms cancel out, so all that's left is this. So what we get is the matrix, so we have a minus out front, actually no, it becomes a plus. Yeah. Okay. And then you have this sum of these nasty partial derivatives of Bij with respect to xk times fj at x star.
Well, why does that become
Because it's a day.
But this whole thing is in braces. I have a minus and a minus.
But
Oh,
no, that's
sorry,
minus, because of the plus.
Yeah,
So
okay,
then, yeah.
okay, so,
Okay.
yeah, I goofed.
I thought I forgot the product rule for a second. I was like, alright, I'm just gonna go with it.
No. I never do that.
Yeah.
You gotta keep an eye on me at all times. No, I forgot I had everything in braces. Okay, so you have this with the minus.
Right.
But, what does this turn out to be though? Because keep in mind what x star is.
So it's G.
X star solves x equals g of x, but what else does it solve?
F of x equals 0.
Yeah,
So then it has to
all
be
these guys are 0. Yeah. So the whole thing
equals
is a 0 matrix.
Uh,
What?
wow.
So that's nice because no matter how monstrous this term was, it had f undifferentiated. So it's going to go to 0 anyway. And everything gets canceled out. So in fact, this canceled out for the same way that the one-dimensional case canceled out. It just was a lot uglier. So at for root, the Jacobian matrix is totally 0.
Oh, this is just at the root. This isn't all the whole.
No,
Okay.
we're not that
I
long.
get that lucky.
Yeah.
Nothing.
Yeah.
Literally.
Yeah. Well, it's kind of amusing how when you have something really nasty like this, you work it out something really simple like 1 or 0. That students actually get outraged, like 1? All that work for 1? or worse, 0. Yeah. So. Okay. So since this whole Jacobian of G is 0 at the root, that means that Newton's method for systems, which I'll describe this way, xk plus 1 is equal to xk plus a vector sk, where sk comes about by solving the system Jacobian of f at xk times sk is equal to minus f of xk. So this says the same thing as up here. Because the thing is, what do we know about inverses? You're not supposed to explicitly compute the inverse. So if you need an inverse of a matrix times a vector, what you're doing is you're actually solving a system of linear equations involving that matrix for that, and your vector you're multiplying by goes here on the right-hand side.
What is SK?
Oh, so SK is a solution of this system of equations, and that goes right here to go from one step to the next. In other words, okay, put it another way, SK is minus the Jacobian of f of xk inverse times f of xk. It's that. Okay. But I'm writing it this way to reinforce the notion that we don't explicitly compute the inverse.
So if this was in code, what would you do?
Oh, you would have this matrix and this vector, and you do a good old backslash. Did I ever come up in lab? Oh, yeah, because in lab, Amber was having you guys write code to do Gauss elimination and so forth. But so in MATLAB language, it's minus your Jacobian matrix backslash your vector, because backslash in MATLAB is for solving a system of equations, and it behind the scenes it does Gauss elimination, the partial pivoting, all the stuff that you were just learning about.
So that's what you use instead of using the inverse.
Right. Yeah. So you do not use, because what you could do is inverse of, so minus inverse of j times f. Don't do that, and MATLAB will warn you that, and it'll work technically, but it's much more expensive because to carry out this operation, I believe Amber covers, if you takes 2/3 n cubed operations for a general matrix. But what this does is it actually solves this kind of system n times, one for each column of the inverse, and then takes that matrix and multiplies it by f. So the cost of this is roughly, well, a lot more, 8/3 n cubed. So mathematically equivalent and a terrible idea. Yeah. So if you do this in your code, MATLAB will give you an orange warning thing and explain that you should use backslash instead. Okay. All right. So before I carry on with Newton's method, so we have these operators. So if you have a backslash b is equivalent to a inverse b, and b can be whatever. It could be a vector. It could be another matrix. So as long as the multiplication operation you want makes sense, it'll do it. On the other hand, if you do a /b, and these are matrices or vectors or whatever, that's the same as a b inverse. Again, as long as the multiplication operation makes sense. Okay. Yeah. So watch your slashes. Okay. Yeah, I should have had Amber bring it up in lab, but I guess since Sue's focused on having you guys know what the methods are.
But I think she did do that.
Probably.
We
Yeah.
had to do n backslash n for like, I mean, we did eigenvalues, right?
Over a step, that's I is a command
I,
for that.
yeah.
Okay. Oh yeah, I guess in iterative methods it came up. Yeah. So in fact, when we were first learning about these things when I was a graduate student at Stanford, but so one thing we would all say is the solution to ax equals b is a backslash b. All these talk in numerical methods is propaganda.
Yeah.
Also, we talk about proof by MATLAB. Like if you prove, if you show that something is true for a random matrix, then it must be true in general. So,
Random matrix.
Yeah,
Generator on
very
MATLAB.
random.
Yeah.
Not very random.
Because it generated, we all used it and it all created the
We all
exact
have the
same one.
matrix.
yeah, that's because MATLAB seeds the random number generator with the same value. So, for instance, if the first thing all you guys do is create the same size random matrix, you have the same numbers. But if you let's say if you do different random things, then eventually you'll see different results. But yeah, since the seed is the same, that's why it wasn't all that random. Yeah, but or at least it's not random across users. So, yeah. In fact, I used to know off the top of my head like what the first few random numbers were that it would generate because I kept seeing them so often. Yeah. So, yeah. Okay. Now. Oh, okay. I was afraid I'd run out of time for things, but it looks like I'm okay. All right. So now I'll more formally describe the algorithm for Newton's methods. That's more conducive to coding it. And we'll see this. Well, I have code on the site, but we'll look at this in code next week in the lab. Okay. So this was solving system of n equations and n unknowns, f of x equals 0. By Newton's method. So first thing you do is you choose your initial guess, x0, and then in a loop up to a certain maximum number of iterations. First, you plug your x value into F. Okay. And then, well, in notes I have a minus, but that seems kind of weird because we always think in terms of y equals f of x. So I won't put a minus here. So then vector sk is minus Jacobian. What's the notes? Okay. Jacobian of f evaluated xk times yk. But as I said before, you wouldn't code it this way. You would solve Jacobian of f at xk. So that matrix times sk is equal to minus yk.
Where did the YK come from on the first? Like if SK ever,
Oh,
because SK,
this is yk.
yeah, okay,
Yeah, I'm just trying to keep each step less cluttered.
right.
Well, I guess it's a bit late for that.
Wouldn't SK be the inverse of the Jacobian?
So when you use backslash?
Well, like I said, this is how I'm writing it mathematically, but this is what you'd really do.
Okay.
There. Okay. So. Okay.
So we make S equals J backslash K, Y.
Minus, yes.
Minus.
All right. And then we just take our vector sk and add it on to a previous x to get our new x. And then you have some sort of if statement to check for convergence. Okay.
This might be a silly question.
Okay.
Okay, so when you're solving the roots in one dimension, you're finding the roots. For a system, are you finding the roots of each equation or of all the equations together?
Okay, so if I write out what this is, we're saying that each component function of f
Okay, so you are finding roots for every
for
single.
all equations simultaneously, yeah.
Okay. But they're independent technically.
Yes.
Okay.
Yeah, well, it's like the example we saw last time where one function traced out a parabola, the other traced out a circle. They have their
They're on separate roots, but they both had roots where they met or the
right, yeah, the intersections.
Yeah.
Yeah.
Intersections.
Yeah, so we're
Not
seeing
objects.
where the intersections of these functions roots are, if any.
So we are finding the intersection.
We can look at it that way. Yeah, because
What those roots are.
yeah, because f1 and 2 at the end are going to have many individual roots that this won't find because they're distinct from one another. Yeah, so any roots in common
Yeah.
because
So the intersection.
it's the same x star.
Okay.
Yeah, so seeing if there's an x star for which all n equations are satisfied simultaneously.
Okay.
And the
So
thing
they're
is,
independent.
yeah, and the thing is, once you get to higher dimensions, it can be very likely for whatever n equation you choose that there are no solutions in common.
This is nice.
Well, like take the parabola and circle example. Like, what if the circle was shifted down a bit or something?
Yeah.
Or you get nothing. So, and then good luck trying to.
So you can do all of that?
Yeah.
Okay.
Yeah. Well, but if there's no root, then
Right.
actually it would be interesting to see what would happen. I mean, it would not converge to anything because there's no hope. But yeah. But as far as what it would produce, well, I guess that would vary from problem to problem. Okay. So actually, let's revisit that example from last time. Having a circle and a parabola intersect. Okay. Okay. All right, so we have, this is our, so basically our f, x1, x2, vector value function, and we have x2 squared, no, x2 minus x1 squared, and then x1 squared plus x2 squared minus 1, and we want both of those to equal 0. So the first one, 0 on a parabola, the other one is 0 on a unit circle. And we saw from the graph last time there were 2 intersections. So fixed point iteration, and I'll demonstrate this next week, it does converge, but slowly, very slowly. And actually, I tried out the idea I mentioned at the end of last time, where if you do this in a Jacobi-like manner, where you don't use any new information about x1 for x2, for instance, yeah, it takes like about 80-something iterations to converge. It's terrible. But if I did a Gauss-Seidel-like formulation where I compute a new x1 and immediately use it to help compute x2, it is still slow, but it cut the number of iterations in half. So that was nice. But Newton's would do a lot better. So for a Jacobian of f, so we're going to take the partial derivatives of these component functions with respect to x1 and x2, and we did that last time. So what we get is, we did it with g. So here we have minus 2x1, and then this would be 1. And then we have 2x1 and 2x2. So that's our Jacobian matrix for this system of equations. And in this case, because it's just a 2 by 2, you could write out what your new iterates are going to be. So our new iterates, so xk plus 1 is equal to xk, which I'll write out component by component, plus, okay, actually, yeah. So I have, I need the inverse of this. So I'm going to have 1 over determinant, so minus 4 x1, x2, minus 2 x1. And then I'm going to swap the diagonal entries and negate the off-diagonal entries. So all of this is Jacobian of f inverse times minus the f values. Oh, this is, I need, what? Oh,
Not just the Jacobian with the minus.
oh,
Not as
well, this minus.
So what part? We just did the.
X1
He's
K.
done the other part of the x with x plus the Jacobian times, like what we did earlier when we moved it around.
Because I thought we just did the Jacobi, the inverse of the Jacobian, which
Yeah.
that part should be negative.
Well,
Right?
you need a minus in there somewhere.
It doesn't really
Doesn't matter where it
Because
goes.
it's multiplied.
That's true. Okay.
Yeah.
We're actually solving
So
for
you got to write just
k
f of
plus
x.
1 equals xk
Yeah.
plus sk, right?
Right.
But then sk
Yeah.
itself is
Yeah. Okay.
this whole thing without the minus is yk. This entire thing is sk. Yeah, so the whole thing's supposed to be minus inverse Jacobian times yk, and I have a minus in there somewhere. So, okay, so we're good?
Yes.
Okay, all right. You didn't sound very certain there, but okay. All right, now, at least this 2x2 case, since the inverse is so easy to work out, it's not really big serious overhead. But for larger matrix, you really should use backslash. Okay, and what we will see in lab is that it actually will converge much more rapidly than either form of fixed point iteration did. But can anyone tell me, from looking at these formulas here, the various entities involved, the iteration breaks down if, so what sort of things would,
X1 K 0.
yeah, like if x1 k equals 0, and let's suppose it's not 0, what else could be a problem?
If we're having 0 matrix,
Oh, I think you said it? Oh. Okay. Yes. So that also will cause the determinant to be 0. Yes, so both cause division by 0 down here. So that's what I was looking for. Minus 1/2. Okay, so you need to be careful to avoid those. So you can't have your Jacobian become a singular matrix. But as long as you avoid that, then at least your iteration can continue. And the thing is, you just want a simple initial guess. Based on what we saw from a graph, you can choose like your initial guesses to both be equal to say 1/2. But it steers clear of these. And it's fairly close to the exact solution in the first quadrant, so it'll
How would
converge
you be
pretty
able to
rapidly.
check that for any function?
Well, yeah, because really you won't know until you try like Gaussian elimination or whatever with your Jacobian, and run into problems there. And also you may have a situation where maybe it's not an exact 0 determinant. Maybe it's not really singular, but it's very close to singular. In other words, ill-conditioned.
Yeah.
So then you're still in trouble because that will lead to slow convergence or no convergence.
Hey, Abdullah, what was that question that we were talking about, the large numbers with ill condition? What's a large number?
Oh, yeah.
And she said yeah.
Oh, yeah, actually,
Sure.
yeah, actually, Amber herself asked me about
Yeah, she
that
said she
later.
was
Yeah, that's
Oh, yeah. Okay,
Is it just
okay.
a judgment?
At
What
what
is the
place
condition number?
it
Yeah.
starts behaving that way?
yeah, it's not a formal notion. It's like, well, it's still a condition if its condition number is greater than such and such. I've honestly never heard something like that. However, I guess you could try to judge it compared to your floating point arithmetic systems specifications, like unit round off and machine precision is on the order of 10 to the minus 16th. So if your condition number is greater than that, you have no accuracy whatsoever. I would say once you start getting territory of like 10 to the 6th, 10 to the 8th, that's pretty bad because then you really can't hope for much accuracy from your computations.
How do you want your condition number to be big so it'd be close to singular?
Oh well, you doing your research, but
But if it's we're talking about if it's ill conditioned or not, right?
yeah. Well, the thing is, since the condition number depends on the ratio between largest and smallest singular values, an ill-conditioned matrix is not necessarily close to singular, or it may be in some sort of relative sense, but maybe not, for instance, the sense you'd be interested in. Also, in your case, you actually want ill condition, it's not a bad thing because you're not actually using that to solve ax equals b. You're trying to find a situation where a singular matrix actually has a non-trivial solution. So, yeah. Yes, we're showing sometimes you do want that, but yeah.
So a well condition may also be close to being singular.
Yeah, like for instance, what if all the singular values are small?
Right. So that's why you look at the residual, right? Or like I mean.
Yeah, well, because the other thing is, this is something that Amber didn't have a chance to cover, because since when you solve ax equals b using whatever method, and so some computed solution x comes out, then you have no way of directly measuring an error.
Right.
So what happens is you have we'll call x tilde what your algorithm actually computes. So that is approximately equal to b. So what you want is the error, I'll call it e, which is the exact solution minus your approximation. You want that to be small, but what you have is a residual, which is b minus ax tilde. And these two are closely related because if I take this equation and multiply both sides by a, then I have ax, which is b, minus ax tilde. In other words, I get the residual. In other words, a times your error is equal to your residual. And what that means is sometimes, depending on the matrix, you could have either one of these be small and the other be large.
Mm-hmm.
So residual is not necessarily a good indicator of accuracy, especially if it's ill conditioned, because depending on what direction this is in, this multiplying by a could drastically amplify it or drastically reduce it. That's what's unfortunate about this is that the relationship is mysterious.
But then if you find the residual, then you can find the error.
Well, that leads to a method called iterative improvement or iterative refinement. You get your residual, and you actually try to solve this system for an error estimate,
Right.
and you can add that onto your solution. It's in the notes. Amber didn't get a chance to cover it; there wasn't time, but it's in there. And it's been shown that suppose you're working in a certain arithmetic system, say like single precision,
Right.
and then you compute a residual using double precision. You can actually iterate this a few times to get the exact solution in single precision. Or like if you are working in double precision but you have extended precision available. So it's actually very effective for that actually wiping out error, if you have the hardware available to give you more precision. So in other words, if you just go ahead and try this like in MATLAB on a regular computer, it's not going to really help you very much. In fact, this whole idea of getting a residual and using this to compute an error estimate is a key ingredient in multi-grid methods. And it's being used by Haley in her research. But in a different context for time-dependent PDEs. But you have a notion of a residual, you have a notion of an error estimate, so you can still do it. Okay, now, last comments on Newton's method. Okay, so the big drawback of Newton's method for systems is in this need to invert to Jacobian every iteration. And I put invert in quotes because, as I said before, you're not actually computing the full inverse of a Jacobian. But what you are doing is you are going to have trouble solving a system of equations every single iteration. It's still expensive. Also, a Jacobian, what makes matters worse is this Jacobian keeps changing every iteration because it's the Jacobian evaluated at xk. Xk is always changing. So in fact, whatever you did from a previous iteration to solve a system, you can't use any of that to help you solve the next system. so this, because normally you think, oh, if I'm going to solve a system several times, I can do LU decomposition once, save the LU factors, and then just use that again and again. But you can't do it here if your matrix is changing. So the fix for this, what?
I'm just kidding. Seeing it.
You don't need to
Yeah.
do it.
Yeah.
Okay, that's actually another issue. Okay, which I don't even mention here. But yeah, you've just highlighted another drawback that's true of regular one-dimensional Newton's method, that you have to compute these partial derivatives. And the secant method is a fix for that. But a fix for this issue, having to invert the same matrix every single iteration, is another method called Broyden's method, which I'm going to cover on Monday, which approximates Newton's method in such a way that you only have to perform an inversion once at the very beginning, and then you keep updating it. And it's actually quite effective. But yes, having to perform a partial differentiation is also unfortunate. So with secant method, okay. So a quick comment about that. You're not having to perform explicit differentiation. You can use a difference quotient, but you're still solving systems, or just for convenience, inverting in quotes, each iteration, since that's still a nagging issue. So Broyden's method would actually, I'll show how it's used, fix Newton's method, where you're still differentiating at the first iteration, and also inverting at first iteration, and then never again after that. And the same idea could be used to fix the secant method, and make it more efficient. So this is something that's not really a big deal for one-dimensional Newton's method, but as you go to systems with more and more equations, it gets out of hand. The nice thing about Newton's method, though, is because it converges so rapidly, often you don't need many iterations. So when you're in methods for solving, for instance, PDEs, partial differential equations, which are described numerically as systems of ordinary differential equations. If they're nonlinear, you have to do something like Newton's method to go from one time step to the next. Or like if you're using you're time stepping using an implicit method, like we talked about early in the semester. Again, you need to do something like Newton's method. So what these methods often do is they just use Newton's method and perform only one iteration. Because it converges so rapidly, you have a good initial guess, your solution for a previous time step, it's already close to what you want. Also, why converge with Newton's method to something that's exact when you already have other error in your solution method, because you have error due to time stepping and a spatial discretization. If you have all these errors, so this is one important principle of numerical analysis in general. If you have error coming from several sources, as you often do, for instance, when working with PDEs, there's no point in solving some subproblem exactly and making that error zero when you already have other error. Not if it's going to cause you much greater computational expense. So make all your errors from different sources at least comparable and save yourself some effort computationally. And that provides the best balance of accuracy and efficiency. So a lot of times, like, you're trying to solve this problem exactly. It's like, well, what for? If having an exact solution to a problem that's wrong isn't really going to help you. So and ends up being a waste of time. Okay, so I will continue with this on Monday with Broyden's method, and then Wednesday we'll be in a lab.
It's Wednesday.
Yes.
Cool.